Hi everyone, this is Gashao. Today we are going to discuss about ways of expressing concentration of solutions. First, as usual, let's see the objectives. At the end of this section, you will be able to define terms like solution, mass percentage, parts per million, and parts per billion of a solute in a solution. The second objective is, at the end of this section, you will be able to calculate the mass percentage, parts per million and parts per billion of a solute in a solution from a given set of information. The third objective is define mole fraction, molarity, equivalent mass, number of equivalents, normality and molality. And the last objective is you'll be able to calculate mole fraction, molarity, normality and molality of a solution from a given set of information and interconvert various concentration expressions. Let's get started. First, there are two qualitative terms. We usually say concentrated solution and diluted solution. So if you have more solutes in a solvent or a solution, we call it a concentrated solution. A diluted solution has less solute in a solvent or in a solution. But in this section, we are going to focus on the quantitative aspects of solutions. We need to quantify how much solute is present in a solvent or in a solution. Let's see the first section about mass percentage, parts per million and parts per billion of a solute. So first, let's define what mass percentage means. Percentage is generally parts per 100. Percent by mass is also called percent by weight or weight percent. It is the ratio of the mass of solute to the mass of the solution multiplied by 100. The equation is percent by mass of solute equals mass of solute divided by mass of solute plus mass of solvent. Mass of solute plus mass of solvent is called mass of solution. Okay, so this is just mass of the solution. Mass of solute divided by mass of solution times 100. That gives us percent by mass of solute. Mass of solute is unitless because the units will be cancelled here. If the mass of solute is in gram, the mass of solution should be in gram, so they will be cancelled out. Because of this reason, percent by mass does not have a unit. Now let's see an example. A solution is made by dissolving 13.5 gram of glucose. Glucose is C6H12O6. The molar mass of glucose is 180 gram per mole in 0.1 kilogram of water. The question is, what is the mass percentage of solute in this solution? So what are the given quantities? The mass of glucose is given and the mass of water is given, right? And you are asked to find the percent by mass of solutes using this formula. Okay, one thing you need to be careful is the mass of solute and the mass of solution should be in the same unit. If this kilogram, you have to convert that one into gram. So 0.1 kilogram is equal to 100 gram. Then mass of solution is just the sum of mass of solute plus mass of solvent. Mass of glucose is 13.5. Mass of solution is mass of solute plus mass of solvent, which is 13.5 gram plus 100 gram times 100. So that gives you 11.9%. That is the percent by mass of glucose. We use percent by mass if the solution is concentrated. When the mass of solute in the solution is very small, parts per million and parts per billion are usually used for very dilute solutions. So the formula for parts per million is mass of solutes divided by mass of solution. If you remember, in the case of percent, we multiply this part by 100, but in the case of parts per million, we have to multiply mass of solute divided by mass of solution times 10 to the power of 6. 10 to the power of 6 is nothing but million. Sometimes you may need to express a mass percentage into parts per million. In that case, mass percentage of solute times 10 to the power of 4, because percentage is 10 to the power of 2. 10 to the power of 2 times 10 to the power of 4 is 10 to the power of 6. So in general, if you are asked to convert mass percentage into parts per million, you have to multiply the mass percentage of solute by 10 to the power of 4. If the solution are very dilute, you can use parts per billion. The meaning of 1 parts per billion is you have 1 gram of solute in a billion gram of solution. Billion is 10 to the power of 9. Okay, So that's the meaning. This is extremely dilute solution. So the formula is mass of solute divided by mass of solution times 10 to the power of 9. 10 to the power of 9 means billion. So we call this parts per billion. The first example, if 150 gram of orange juice contains 120 milligram of ascorbic acid or vitamin C, what is the concentration of ascorbic acid expressed in parts per million and parts per billion? So what's given here? We have mass of ascorbic acid, which is 120 milligram, and mass of orange juice is 150 grams. So we can consider this as mass of solution. This is your mass of solute. But one thing you need to be careful is the units should be the same. This is in gram, this is in milligram, so everything should be in gram. So if you convert this milligram into gram, you have to convert this prefix milli, which is 10 to the power of minus 3. So this becomes 120 times 10 to the power of minus 3 grams. So don't forget that prefix. So what you can do is to find parts per million, 120 times 10 to the power of minus 3 gram divided by 150 gram times 10 to the power of 6. So if you do that, you will get 800 parts per million. To convert this into parts per billion, just multiply this by 1000. So that gives you parts per billion. So parts per million of vitamin C, the ones that you got over here, times 1000 gives you parts per billion. Because billion is 10 to the power of 9 and million is 10 to the power of 6. So they are related using this equation. Now let's see the second question. In the United States, the maximum allowable concentration of lead in public drinking water is 0.015 milligram per liter. Convert 0.015 milligram per liter to parts per billion. So you need to convert this concentration to parts per billion. Now let's convert that one. First thing is we need to convert this milligram into gram. So if you convert that, this becomes 0.15 milligram, which is equivalent to 0.015. Milli is a prefix, 10 to the power of minus 3, 10 to the power of minus 3 gram. So this is a gram. We can also convert the volume of the solution, which is 1 liter, right? This is milligram per liter. So 1 liter is 1000 milliliter. In this case, the amount of solute is extremely small, so we can say that this volume is the volume of water. So if you remember, the density of water is 1 gram per milliliter, which means 1 milliliter is 1 gram. That means 1000 milliliter is equal to 1000 gram. So if you put that into the formula, this is mass of the solution and this is mass of the solute times 10 to the power of 9. So we have 0.15 times 10 to the power of minus 3 gram. This is mass of the solute. The mass of solution is a liter, which is 1000 gram, times 10 to the power of 9. This is for parts per billion. This is billion. So in that case, you will get 15 parts per billion. What does this mean? The maximum allowable concentration of lead in drinking water is 15 parts per billion. This is in the United States. So this is how you calculate parts per billion from milligram per liter. The second type of concentration unit is mole fraction. When you consider mole fraction, we have to consider the two types of solutes, non-electrolytes and electrolytes. So the formula is a little bit different. For non-electrolytes or non-electrolyte solutes, the mole fraction of the solute is equals to the number of moles of solute divided by number of moles of solute plus number of moles of solvent. You can write mole fraction as x of solute equals number of moles of solute divided by number of moles of solute plus number of moles of solvent. So you can calculate the mole fraction using this formula for non-electrolytes. How about for electrolytes? In the case of electrolytes, when you put them in water, say for instance, they will dissociate to give you ions. So you have to consider ions. So you'll consider cations and anions. So you need to calculate the mole fraction of the cation and the mole fraction of the anion. So to calculate the mole fraction of the cations, you have to use this formula. Mole fraction of the cations equals number of moles of cations divided by number of moles of cations plus number of moles of anions plus number of moles of solvent. For the anions, also mole fraction of the anions equals number of moles of anions divided by number of moles of cations plus number of moles of anions plus number of moles of solvent. So the formula is a little bit different. Let's work with some examples. The first example determines the mole fraction of the substances in a solution containing 36 grams of water. Molar mass of water is 18 grams per mole, and 46 grams of glycerin, which is molar mass 92 grams per mole. So here the masses of the solute and the solvent are given, and the solute, in this case glycerin, is non-electrolyte, so you have to use a simple formula. But first you need to calculate the number of moles of water and number of moles of glycerin. The molar masses are given over here, so just raise the number of moles. Given mass of water, which is 36 grams, divided by 18 grams per mole. In that case it gives you 2 mole. For glycerin, 46 divided by 92, which gives you 0.5. To calculate the mole fraction of water, you have to use this formula. Mole fraction of water equals number of moles of water divided by total number of moles. Okay, this is 2 divided by 2.5, which is 0.8. To calculate the mole fraction of glycerin, since you have only 2 components, you can subtract the mole fraction of water from 1. In that case you'll get the mole fraction of glycerin, but you can also use a direct formula. Mole fraction of glycerin equals number of moles of glycerin divided by total number of moles, which is 0.5 divided by 2.5. you get 0.25, or you can just subtract 0.8 from 1. In that case you'll get mole fraction of glycerin. 1 minus 0.8, you'll get 0.2. So you'll get the same results in both cases, but this one is easy because you already calculated the mole fraction of water. Just subtract that from 1. So this is an example for non-electrolytes. Let's see for electrolytes. You have, say for instance, 0.1 mole of sodium chloride dissolved in 10 moles of water. Calculate the mole fraction of sodium ions and chloride ions. So in this case, this is a strong electrolyte. So when you dissolve sodium chloride in water, if you have 0.1 mole of sodium chloride in water, you will have 0.1 mole of sodium ion and 0.1 mole of chloride ion. So you have to consider that one. So which means if you dissolve sodium chloride 0.1 mole, this will give you 0.1 mole of sodium ion, which is a cation, and 0.1 mole of chloride ion. So if you are asked to find the mole fraction of sodium ion and chloride ion, so you have to use these moles. Let's see the calculation. So mole fraction of sodium ion is number of moles of sodium ion, we have 0.1, divided by the number of moles of sodium ion plus number of moles of chloride ion plus number of moles of water. This is a solvent, so just plug the values. 0.1 plus 0.1 plus 10. This gives you the number of moles of sodium ions. To get the chloride ions, you can use this formula, and since the number of moles are the same, you get the same mole fraction. The mole fraction of water is given by using this formula, number of moles of water divided by this total number of moles. So in that case you'll get 0.98. So the take home message here is, if you have electrolytes, you can calculate the mole fraction of the cations and the anions. If you have non-electrolytes, you can use a simple formula. The mole fraction of the solid is just simply number of moles of the solid divided by the total number of moles. But in the case of electrolytes, you have to consider the mole fraction of the cations and the anions, because when you dissolve ionic compounds in water, say for instance, they will dissociate to give you the cations and the anions, and you can calculate the mole fraction of the cations and the anions using this kind of formula. The other important concentration unit is molarity. Molarity is defined as the number of moles of solute divided by the volume of the solution in liter. Okay, so this is a formula: number of moles of solute divided by the volume of the solution in liter. And number of moles is given by mass of solute divided by molar mass. So if you plug that number of moles with mass of solute and molar mass of solute, if you replace the number of moles of solute by mass of solute and molar mass of solute, so you'll get this equation, which is mass of solute divided by molar mass of solute times volume of the solution in liter. So you can use this formula to calculate molarity. So molarity is the most commonly used concentration unit. So now let's see an example. In this example, you have 5.85 gram of sodium chloride. Molar mass is 58.5 gram per mole, is dissolved in 250 milliliter of water solution. Now the question is, calculate the molarity of the solution. The mass of sodium chloride is given, the volume of the solution is given, which is 250. Always, if the volume is given in milliliter, we need to convert that into liters. So 250 milliliter is equal to 0.5 liter. Molar mass is already given, so we can just plug them using the molarity formula. Mass of sodium chloride 5.85, molar mass of sodium chloride 58.5. The volume of the solution in liter is 0.25. So if you plug that values, okay, if you plug them, you will get 0.4 mole per liter or 0.4 molar. So that is the concentration of sodium chloride. If you dissolve 5.85 gram of sodium chloride in 250 milliliter of water solution, you will have 0.4 molar sodium chloride solution. The other concentration unit is normality. Normality is defined as the number of equivalents of solute divided by volume of solution in liter. So here you have number of equivalents of solutes. Now what is the number of equivalents of solute? Number of equivalents of solute equals to measured mass or mass of solute divided by equivalent mass. Now we have another question. What is equivalent mass? Equivalent mass is molar mass divided by N. What is N? So we know molar mass. So what is N? N varies from compound to compound. The value of N depends on the nature of compound. Now let's see for acids and bases. For acids and bases, N equals to the number of ionizable hydrogen ions. For bases, number of ionizable hydroxide ions. Now let's see example. If you look at sodium hydroxide, when sodium hydroxide dissolves in water, it gives you sodium ion and hydroxide ion. So it gives you one hydroxide ion, which means in the case of sodium hydroxide, N equals to 1. For sulfuric acid, say for instance, when sulfuric acid dissociates in water, it gives you 2 hydrogen ion and sulfate ion. So which means N is equals to 2, because for acids and bases, N equals to the number of ionizable hydrogen ions for acids and hydroxide ions for bases. So in this case, for sulfuric acid, N is 2. For phosphoric acid, has 3 ionizable protons. So in this reaction, say for instance, only 1 hydrogen ion is ionized, so N equals to 1. In this case, there are 2 ionizable hydrogens, so N becomes 2. In the third case, we have 3 ionizable hydrogens, so N equals to 3. So in general, for acids and bases, N equals the number of ionizable hydrogen ions for acids and number of ionizable hydroxide ions for bases. So you need to remember that to find N. For ionic compounds, for salts in general, N equals to the total charge carried by the cations. Say for instance, in the case of sodium chloride, you have sodium ion and chloride ion. Sodium ion, you have only 1, N is 1. For aluminum sulfates, if you look at aluminum sulfate, you have 2 aluminum 3 plus, so 2 times 3 equals to 6. So the total charge carried by the cation in this case is 6, so N becomes 6. For oxidizing and reducing agents, N equals to the total number of electrons gained or lost. Let's say an example. This is permanganate. Permanganate gained 5 electrons and reduced to manganese plus 2. Since 5 electrons are gained, if you are asked to find the equivalent mass of potassium permanganate, say for instance in this reaction, this becomes 158 gram per mole, which is the molar mass of potassium per manganate, divided by the number of electrons gained. In this case is 5 equivalent per mole, so it becomes 31.6 gram per equivalent. For oxidizing and reducing agents, you have to consider the number of electrons gained or lost. So the value of N varies from compound to compound in this case. One thing we need to remember is that normality is molarity times N. Normality is always equal to or greater than molarity. So we need to remember this. Normality equals molarity times N. We said that N is the number of ionizable protons for acids, the number of ionizable hydroxide ions for bases. N equals the total number of positive charges for salts, and also for redox reaction we have to consider the total number of electrons lost or gained during a redox reaction. Always normality is equal to or greater than molarity, because n could be 1 and above that. If n is 1, normality equals to molarity. Let's say example. Calculate the number of equivalents present in 0.5 mole of phosphoric acid if the acid is completely neutralized to give phosphate ion. In this case, all the 3 hydrogen ions are removed, which means n is 3. So you need to multiply the number of moles by 3, which is 1.5 equivalents. Be converted to dihydrogen phosphate. In this case, you have only one ionizable proton. N is equals to 1, which is the same as 0.5 times 1, the same 0.5 equivalents. In the third case, you have hydrogen phosphate. In this case, there are 2 ionizable protons. You have to consider 2 ionizable protons. N equals to 2. 2 times 0.5 equals to 1 equivalents. Let's see another example. Calculate the molarity and the normality of 49 gram of sulfuric acid in 500 milliliter of solution. So what is given here? The mass of sulfuric acid and the volume of the solution. We know that the molar mass of sulfuric acid is 98 gram per mole. The mass of sulfuric acid is 49. Volume is 500 milliliter. The volume is always in liter. If milliliters are given, you need to convert that milliliters into liters. So in this case, you have 500 milliliter. So that is equal to 0.5 liter. We are asked to find molarity and normality. So first, let's calculate molarity. We know that molarity is equals to the number of moles of solute divided by volume of the solution in liter. The mass is given 49 gram, and we know the molar mass of sulfuric acid is 98 gram per mole. If you divided that times 0.5, this gram will be cancelled by gram. It becomes mole per liter, which is just 1 mole per liter, 1 molar. In this case, we are assuming that sulfuric acid has 2 ionizable protons. N equals to 2. Normality equals molarity times 2. Then it becomes to normal. So this is how you calculate the molarity and the normality of sulfuric acid solutions. Normality is equal or greater than molarity. This is always true. The last concentration unit that we are going to see is molality. Molality is defined as number of moles of solid divided by the mass of the solvent in kilogram. If you remember, for normality and molarity, we use the volume of the solution. In this case, we are considering the mass of the solvent, not the solution. So here, the mass of solvent in kilogram. So we know that number of moles of solute is mass of solute divided by molar mass, which is times mass of solvent in kilograms. So we can use this formula to calculate molality. What is the advantage of using molality? Molality is independent of temperature, but both molarity and normality are affected by temperature changes. Here, in the case of molality, we are considering the mass of the solvent. In the case of normality and molarity, we use volume. Volume is affected by temperature. If there is a temperature change, the volume of the solution may change. So if you increase temperature, say for instance, it might expand. Expansion may be possible, so the volume may increase. In the case of molality, we are considering mass of solvent. Mass of the solvent is not affected by temperature changes. So that is a very useful property for molality. So molality has advantages because its value doesn't change when temperature changes, but for normality and molarity, the values change as temperature changes because volume changes as temperature changes. What is the molarity of a solution made by dissolving 34.23 gram of table sugar, sucrose, in 400 milliliter of water? The molar mass of sucrose is 342.3 gram per mole. First, we need to list down the given values. Mass of table sugar is given. Molar mass of sugar is given. You have 400 milliliter, which means 400 gram, because the density of water is 1 gram per milliliter. So if you have 400 milliliter, obviously that equals to 400 grams. We need to convert the mass in gram into kilogram, which is equivalent to 0.4 kilograms. So if you plug all these values into the formula, mass of solute, which is 32.23 gram, molar mass of sucrose 342.3 gram per mole, and the mass of solvent in kilogram is 0.4, because this gram will be cancelled by gram, so it becomes mole per kilogram. That is equal to 0.25 mole per kilogram, or 0.25 molar. So this is how you calculate the molality of a solution from mass of solute and mass of solvent. So the last topic that we are going to discuss is conversion of concentration units. It is possible to convert one concentration unit to the other. If the density and the volume are given, you can calculate mass from this formula. If the mass and the density are given, you can calculate the volumes. The other thing you need to remember is molality involves the quantity of solvent. For the other, like normality and molarity or percentage, we need to know the quantity of the solution, the volume in solution for normality and molarity. But for percentages, you need to know the mass of the solution. Now let's see an example. A solution of hydrochloric acid in water, molar mass 18 gram per mole, contains 37% hydrochloric acid. Molar mass is 36.5 gram per mole by mass. So this is percent by mass. And the density of the solution is 1.18. So the density is given, the mass percent of HCl is given. Using this information, we are asked to find mole fraction of HCl in the solution, molality of HCl in the solution, molarity of the solution, normality of the solution. So we are asked 4 questions to answer based on 2 informations. We are just given percent by mass and density of the solution. So let's see the strategy. What does percent mean? We need to understand what percent means. Percent means parts per 100. If you have 100 gram of the solution, this solution contains 37 gram of hydrochloric acid and 63 gram of water. So if you add them, these two, you'll get 100 gram. This information basically is enough to calculate the mole fraction and molality, because we have mass of the solute and mass of the solvent. If you have this, you need to find the number of moles, and then from that you can calculate mole fraction. That's for mole fraction. For molality, we have the mass of the solute, so we need to find the number of moles of solute, and then we need to divide that by the mass of the solvent in kilogram. So this information is enough to solve the first 2 problems. First, let's calculate A. A is the mass is 37 gram divided by the molar mass of HCl, which is 36.5 gram per mole. This gram will be cancelled by gram, so you'll get 1.01 mole. For water, you have 63 gram divided by 18 gram per mole. This is the molar mass of water, so you'll get 3.5 mole. So the mole fraction of HCl equals number of moles of HCl, which is 1.01, divided by total number of moles. Just add these 2 moles and then divide that, you will get 0.22. This is the mole fraction of HCl. Okay, this is how you calculate the mole fraction of HCl. How about the molality of the solution? We have already number of moles of solute here, 1.01, right? So we need to convert the mass of the solvent into kilogram, which is 0.63. 63 gram is equals to 0.063 kilogram. We have the number of moles of solute, which is 1.01 over here. So if you plug that, 1.01 divided by 0.063, that gives you 16.03. So this is how you calculate molality. For the 2 questions, we need to calculate the volume of the solution. So we have 100 gram of the solution. We know the density is given. So to calculate the volume of the solution, mass of the solution divided by the density of the solution. So this is the density. That gives you 84.75 milliliter. But when you calculate molarity and normality, always the volume should be in liter. Don't forget that one. So divide this by 1000. In that case, you'll get 0.08475 liter. So this is the volume of the solution in liter. Once you get this, we have the number of moles already. Just plug the values. Number of moles of HCl divided by volume of solution in liter. This is the number of moles of HCl. This is the volume in liter. So you'll get 11.9 molar. This is the molarity of HCl. We know that hydrogen has only 1 ionizable proton, so N should be 1. So molarity times 1 gives you the same value, which is 11.9. In other words, molarity and the normality of the solution is the same in this case. Now let's finish this section by working on these review questions. The first question is, a solution of sulfuric acid in water contains 98% sulfuric acid by mass, and the density of the solution is 1.84 gram per milliliter. Calculate the mole fraction of sulfuric acid in the solution, the molarity of the solution, the normality of the solution. Assume that sulfuric acid has 2 ionizable protons. Actually, this is a very concentrated sulfuric acid. It may not ionize to give you 2 hydrogen ions, but let's assume that it gives you 2 hydrogen ions for calculation purpose. We have to follow the same procedures that we used previously, if you remember. As usual, pause the video and try to solve these questions. So when you are done, play the video to see the solution. 98% biomass of sulfuric acid means if you have 100 gram of the solution, 98 gram is sulfuric acid, 2 gram is water. That's the meaning of this 98% sulfuric acid. So if you take 100 gram of the solution, 98 gram becomes sulfuric acid, 2 grams becomes water. The density is also given. So from that we can calculate volume, because mass is already known here. So we know that percent means parts per 100, right? This is 100 gram of the solution contains 98 gram of sulfuric acid and 2 gram of water. That's the meaning of this 98% sulfuric acid biomass mean. So the density of the solution is also given. From this we can calculate volume. To calculate mole fraction, we need to calculate the number of moles of solute and solvent. That's what we need to calculate mole fraction. To calculate the moles of sulfuric acid, we have the mass, which is 98 gram. 98 gram per mole is the molar mass of sulfuric acid. This gives you 1 mole. For water, you have 2 gram. 2 gram divided by the molar mass of water, 18 gram per mole. This is 0.11 mole. Then next thing is we need to calculate volume, because we need volume to calculate molarity and normality. Since we know the mass of the solution is 100, we took 100 gram of the solution, we divided that by the density. In that case you will get the volume. This is it should be 100 gram divided by 1.8 gram per milliliter, not mole. This should be milliliter, not mole. So in that case you'll get 54.35 milliliter, which is equals to 0.05435 liter. So that is the volume of the solution. If you plug the values, the mole fraction of the sulfuric acid equals number of moles of sulfuric acid divided by total number of moles, 1 divided by 1.11, which is 0.9. This is the mole fraction of sulfuric acid. The next question is the molarity of the solution. The third one is the normality. We have already the number of moles of sulfuric acid, which is 1. The volume of the solution in liter is 0.05435. Just if you divided this, you'll get 18.4 mole per liter, which is 18.4 molar. So this is a molarity of sulfuric acid. To find normality, we have to assume 2 ionizable protons, so we need to multiply the molarity by 2. So in that case it becomes 18.4 times 2, 36.8 normals. You can also calculate it using the normal formula. Equivalent weight of sulfuric acid is 98 divided by 2. 2 is the number of ionizable hydrogens. So in that case you'll get 49 gram per equivalents. Then if you divided that with mass of sulfuric acid, which is 98 gram divided by 49 gram per equivalence, because the equivalent weight is already over here. So in that case you'll get 2 equivalents, divided that by the volume of the solution, you will get 36.8 normal. So the values will be the same. Now let's see the second question. At 0.1 molar glucose molar mass is given 180 gram per mole. Aqueous solution has a density 1.14 gram per milliliter. Calculate A, the mass percent of glucose, B, the molality of glucose, C, the mole fraction of glucose. In this case, so what is given is concentration in molarity and density. So based on that information, you are asked to find the mass percent of glucose, the molality of glucose, and the mole fraction of glucose. So as usual, just pause this video and try to solve these problems, and when you finish, play this video. In this case, the density is given, the molarity is given. If you take 1 liter of the solution, it contains 0.1 mole of solute. In 1 liter of solution, or 1000 milliliter of the solution, you have 0.1 mole of glucose. That's the meaning. If you consider 1 liter of the solution, you can calculate the mass of the solution using the volume, because density is given over here. The mass of solution is density times volume. The density is already given over here, 1.14 gram per milliliter times 1000 milliliter. Milliliter will be cancelled by milliliter, so you'll get in gram. Just multiply this. That gives you 1140 gram. This is the mass of the solution. From this we need to get the mass of solute. The mass of solute is simply 0.1 mole times the molar mass of glucose. That gives you 18 gram. From this solution, 1140 gram of solution, 18 gram is glucose. So how about the solvent? To get the mass of the solvent, you need to subtract 18 from 1140. That gives you the mass of the solvent. 1140 gram minus 18 gram, that gives you 1122 gram. This is the mass of water. If you convert that into kilogram, because we need this kilogram to calculate molarity, so that gives you 1.122 kilogram. To calculate the number of moles of solvent, mass of solvent, we have here, which is this much gram divided by 18 gram per mole. Gram will be cancelled by gram, so you'll have 62.3 mole of the solvent. Now we have all the information. We just simply plug them. Mass of solute divided by mass of solution times 100 gives you the mass percent of glucose. We know that the mass of glucose is 18 gram times 100 divided by mass of solution. We already got using the density of the solution, so 1140 gram is the mass of the solution, so these units will be cancelled. That gives you 1.58%. so that is the mass percent of the solute or glucose. B, molarity of glucose. We already know the number of moles of solute, in this case is 0.1. We also calculated the mass of solvent in kilogram, which is 1.122 kilogram. This gives us 0.089 mole per kilogram, which is called molar. Small m means molar. Third one is mole fraction of glucose. Mole fraction of glucose is number of moles of glucose divided by total number of moles. So the moles of glucose, we got 0.1 mole divided by total number of moles. This is the number of moles of water, 62.3 mole plus 0.1. So that gives you 0.002. That is the mole fraction of glucose. That is it for today. I'll see you in the next video.